Hello and welcome, my Chicago friends. Thanks for joining us today. I will be talking about primer on NoSQL databases for developers. As we say in Microsoft, developers. So I am a consultant. I'm in the consulting arm of Microsoft. My primary focus is on Azure. So basically, I work on the retail side of the customers, and I do everything from onboarding retail customers to Azure to preparing them for Black Friday. And some of the lessons learned from the field are what I'm sharing with you today. I am primarily focused on infrastructure slash DevOps, but I also work with quite a bit of databases. And before I joined Microsoft, I used to be a Microsoft MVP, which I had to give up when I joined Microsoft. And back then, my primary focus was a lot of databases on Azure. So that's how I got my MVP. So as a result of that, I'm quite well versed in different types of databases and how to pick them. So that's what I'm sharing. Like David mentioned, I am also the organizer of the Orlando.NET user group and organizer for the Orlando Code Camp, which is based in, actually, it's scheduled to be held on March 25th. So if anyone feels like coming down to Orlando in March, it's not a bad time to be there. If you want to connect with me, those are my handles on LinkedIn, GitHub, Twitter, and Mastodon. So feel free to hit me up on any of these. LinkedIn is probably the best professionally. Also, I do share quite a bit on LinkedIn and other social media. The content for today's talk. So most, if not about 95 to 99% of the content is probably available at this particular link. So you can either type that link into your browser, or you can just take a photo of the QR code, and that should take you to the link above. So in today's talk, I will be talking about what is NoSQL database, and then I'll be talking about what problems, what are some of the problems that we face as developers, and how does NoSQL solve those problems? As a result of that, I'll be diving into NoSQL fundamentals. We'll talk about the types of NoSQL databases, data modeling in NoSQL, and then what are some of the factors to consider when we transition from SQL to NoSQL? Because I'm guessing that at least a good portion of the audience is SQL-based audience. So, I'll be talking from that perspective because my primary, database used to be SQL Server, and then I started working with quite a bit of NoSQL databases. So I can kind of speak about that transition. If anyone has any questions, how should I handle that? That's a good. And do you want to come off mute and talk to me, or how do you want me to handle that?
We've done it, kind of anyway. If people want to come off of mute and kind of raise their hand, that's fine. Some people prefer to put a question in chat. Like I say, we kind of monitor chat and we'll holler if there's something in there. So, yeah.
Sure.
So
yeah. So feel free to interrupt me if there's someone in chat, because of my setup, I'm finding it hard to load chat. But yeah, okay, I can kind of see chat, so we should be fine. But if I'm not noticing something and moving on, feel free to interrupt me. Cool. So what I would like to do is, give me 1 second. I want to get my screen set up so I can. All right. So let's talk about, let's start by talking about what is NoSQL. NoSQL is basically non-relational data. So most of us who got started in the .NET SQL Server era are more familiar with tabular/relational databases. But over here we'll be talking about non-relational or non-SQL data. This basically indicates the storage and retrieval mechanism. And as a result, the modeling of this data is different compared to the one type of relational tabular databases that we're used to. Even though this type of data storage has been around for the last 10, 15 years or more, it's become more proliferated with the rise of all the e-commerce/social media type products, and all the sharing services, the Netflix and all of that have definitely contributed quite a bit in the rise of NoSQL databases. NoSQL also refers to not only SQL. This emphasizes that some of them may support SQL-like query languages, but not SQL-like storage, if that makes sense. So what problems do NoSQL database solve? We'll be talking about two different issues that are primary issues that are solved by NoSQL systems: impedance mismatch and scaling. So let's talk about impedance mismatch. So let's take this particular diagram as an example. In this diagram, to create the single user object using database normalization techniques, we write the data to 6 different rows in 3 different tables by normalizing that single block of data. And then to read the data, we have to read those 6 rows spread across 3 different tables. Now, this is just a simple example of a user record. And now, if you work with any kind of moderately complex tabular or SQL database, these type of read-write operations for user records easily involve dozens upon dozens of tables. So this read and write that is done by disassembling and reassembling object is kind of inefficient, right? I mean, for single record, you're going across 6 rows across 3 tables. Now imagine doing this at scale. So when you do this at scale, it manifests itself in higher resource consumption. So the problem with SQL databases is that the hardware and software are usually optimized for one scenario, which is storage. And this comes from the history of SQL databases. SQL databases basically came around because we had back in the day, like, the 60s, 70s, 80s, storage was at a premium. So we had to figure out how to efficiently store data. And then retrieval kind of came after that. So SQL databases are usually optimized for storage, but the retrieval part is where we experience issues. ORM frameworks, or object relational mapping frameworks, address these issues, and they do this by abstracting out the whole storage and retrieval part. But the fact still remains that behind the scenes, they are doing all these disassembling and reassembling of data, which leads to reduced speeds. So NoSQL, in a simple slide, right? If I had to sum it up in a simple slide, NoSQL basically eliminates this impedance mismatch by In this case, it employs a document-oriented NoSQL database. And instead of storing it in 6 different tables across, 3 different tables and 6 different rows, it stores it as a single JSON document. So it makes storage and retrieval extremely fast. Now, keep in mind that there are downsides to this, and which we'll be talking about. So NoSQL eliminates the impedance mismatch because the reads and writes, as you can see, they involve a single JSON document. It simplifies application development since disassembling and reassembling of object are no longer required. And it also removes the need for ORM frameworks. Let's talk about scaling. So relational databases are basically vertical scaling, which means that the databases scale up to match peak system loads. And when I say peak system loads, I'm talking about the total number of concurrent connections. Traditional methods of scaling involve basically scaling your system hardware up to meet the system load. Now, this approach is fraught with issues. For instance, the upper bound on hardware specifications. So, you can keep increasing your RAM, CPU, hard drive, and so on, but there's an upper bound on that. And then there's also the other issue is the machine itself serves as a single point of failure, because if the server fails, maybe you have like another replica, but that's still quite a complicated operation. NoSQL databases, on the other hand, are designed to store data and distribute the load across multiple nodes. These nodes are usually commodity hardware, which are optimized to perform for data sizes. So for instance, if you look at a lot of NoSQL databases, they are run on small commodity VMs that store up to 10 gigabytes of data. And this is because everything on there is optimized to handle the storage and retrieval of 10 gigabytes of data. And you can do that, if you know what exact data size is. So as the application load increases, the system basically keeps adding nodes, i.e. it scales horizontally. The added benefit of this type of architecture is that when an individual node fails, the other non-failing nodes can keep responding. There's no single point of failure. This greatly increases it reduces the single point of failure risk, and it enhances the availability of the database system. So, a couple of things to keep in mind. While you're gaining availability, you're also losing something, which is with SQL databases, you have the concept of atomicity, consistency, isolation, durability, or ACID, and you're kind of violating the ACID principles when it comes to storing data across multiple nodes. And we'll discuss that in a couple of minutes. Any questions so far? Okay, cool. So we will dive into some fundamentals for NoSQL. First is CAP theorem and 3 V's. So what is CAP theorem? CAP theorem is also known as Brewer's theorem. So the previous slide, I talked about how you're violating the ACID principles. And part of that ACID is atomicity consistency. So we're basically talking about consistency in this slide. So consistency of data is a huge trade-off when you're talking about NoSQL databases. Like all distributed systems, NoSQL databases are subject to this CAP theorem, which states that it is impossible for a distributed data store to simultaneously provide more than 2 out of the following 3 guarantees. So you can see the 3 guarantees on the screen. Consistency, which means that every read receives the most recent write to the system, or it throws an error. So that's consistent. So you can either, when I write a value X to the system in a row, and I try to retrieve that row, it should return X, or it should say, I'm not able to return anything. So that is consistent. Availability is every request receives a non-error response. So in consistency, if it's not able to retrieve it, it throws an error. In availability, it will return some kind of value, which may not be the latest one. And partition. Partition tolerance means that the system continues to operate despite an arbitrary number of messages being dropped by the network. So for instance, there's a cable cut, the system should continue to operate. So summing these 3 up, Brewer's theorem says you can either be consistent and available, or consistent and partitioned, or available and partitioned. You can only get 2 of these 3. So that's CAP, but there is an additional level to this CAP theorem. The CAP theorem implies that in the presence of network partition, i.e. when the network loses connectivity, we must choose between being consistent and available. But networks are never reliable. Networks are never 100% reliable. So the reality is we must always tolerate partitions in a distributed system. Fortunately, we get to choose this type of trade-offs when a partition does occur, and this is known as the Pacular Theorem, or PACELC. And you can kind of read the definition on the screen, which states that in case of network partition in distributed system, you must choose between availability and consistency, even when the system is running normally, in the absence of partition, one has to choose between latency and consistency, which means you have to always account for a system experiencing network partitioning, and you have to choose whether I am okay with slower speeds, or if I'm okay with fast speeds, but my data being inconsistent. So that is the Pacular theorem, and that's kind of the basis of today's talk. So if you don't take anything else away from today's talk, I hope that these basics that talk about what CAP theorem is and how we build on the CAP theorem, and we basically choose between latency and consistency for NoSQL databases, is kind of what I hope that you can take away. So to discuss this Pacular theorem further, I want to kind of give you two illustrations. So let's take the one to the my left, which would also be your left, I think. So in this scenario, the system has updated the node to the left. Sorry. Yeah, system updated node 1. So node 1, you see value 1 has a value of A, but node 2 still has the old value, which is C. So what happens is, as soon as the system updates node 1, there's a network partitioning, i.e., there's some kind of issue with the network. So because we are, if we're choosing for consistency, any kind of application that tries to access node 2 would know that node 2 has inconsistent data in it, and it will get an error. So that is, when you make the system consistent, this is what you have to, this is the trade-off. So a good example of this is inventory systems. So, I work a lot with retail e-commerce type vendors, and in retail or in e-commerce, it is okay for the inventory to show 0 or throw an error saying inventory is not available. But you should never promise a customer that something is available and it not be available because the system did not properly sync the latest inventory count. So this is an example of wanting consistency in your system. Same thing for bank records. So I don't want my bank record to say that I have money that I don't, or vice versa. Now, let's shift to the scenario to the right. In this scenario, the system it's the same issue, right? The system has updated the node to the left. The node to the left has value 1 says A. And when it tried to update the node to the right, at that point, there was a network partition, so the node to the right could not be updated. So what? But we are saying that I want my system to be available 100% of the time. So in this case, when the application comes in and tries to read the stale node or the node 2, it will return a stale value. It's fine. It says value C. When you try to get value 1, it'll return C. And this is fine. In certain types of systems, it's okay to get stale data. For instance, let's say I have a social media system, and what it's doing is it's updating the number of likes, and it did not get the latest count of likes. And when my UI came and read the number of likes, it showed an old stale number. It's fine, it's not the end of the world. So in this case, what they're doing is they're making sure that the system works fine, and the system is available, and it returns some data, even if it's stale data. So on the left, we chose for the system to be consistent and threw an error when it tried to access stale data. On the right, we choose for the system to be available. So when it tried to access stale data, it returns stale values. Excuse me. The second thing I want to talk about for NoSQL fundamentals is the 3 V's. And the 3 V's are volume, velocity, and variety. So this is very important when understanding NoSQL data. Where people use the term NoSQL, big data, and all of these pretty interchangeably. So this leads us to believe that every time you say big data, that the only criteria for a data set to be classified as that is for the data set to be massive. That is, for it to be petabytes of data or terabytes of data. But I want to posit that large volumes of data do constitute a big data. So particularly data sets measured in terabytes, petabytes, because these present unique challenges in terms of storage and processing. Additionally, the issue with such voluminous data sets is that search algorithms that works fine on smaller data sets may not operate as efficiently on these massive data sets. Oops, excuse me, jump too far. But there are also other criteria that qualifies for things to be NoSQL or big data. For instance, velocity. So you may not have terabytes of data coming in, but you could be getting slammed with real-time data or near real-time data from things like IoT devices and so on. So let's take an example of data generated by a self-driving car. So a self-driving car might slam you with with data at real time, but then when you turn the car off, there's no data being generated. So collecting this data becomes a challenge, collecting and processing this data instantaneously. So if you're driving if you have a self-driving car, you want to not only collect this data, but you want to process it near real time. So this is a unique challenge as compared to storing petabytes of data. So high velocity data is definitely another thing that you have to consider in terms of testing the responsiveness of your system. And finally, variety. Most of the data that we were used to in older systems was text or tabular based data. But these days we are also having to deal with media type data, unstructured data, and so on. So these are different in that you cannot run your traditional SQL queries and joins and other things on these data. So it does test the responsiveness of your system. So that would also classify as big data. Now let's talk about the different types of NoSQL databases. You're certainly used to SQL databases like SQL Server, MySQL, Oracle, and so on. But there's also a whole other family of databases, and these are some of those. So we'll talk about them one by one. So the first one is a key-value database. So this is an example of a key-value database. As you can see, the data is inserted as key-value pairs. So on the left, you have a key, right, you have a value, and you can read the data using the key. So the whole caveat to this is when you're reading the data, you get a O of one lookup. So if a lot of job interviews ask us about what is the efficiency of this algorithm, and obviously the most efficient algorithm is O of one, and key value databases achieve O of one lookup by using the record key plus a partition key. So in NoSQL databases, as you know, databases can be stored on multiple nodes. So each node is a partition. So not only do you have to provide the key of the record, but also the key of the partition to achieve these type of speed. But once you do that, you get O of one lookup speeds. The data is flexible schema, which means that you can store anything from primitive data types like strings to JSON type data to even blobs in certain cases. The key value type basically uses a hash table in which there exists a unique key and a pointer to an item of data. Key value databases often operate by storing data on volatile memory, i.e. RAM, or SSDs. So this is how they achieve their speeds. The simplicity of this scales really well, but you cannot have real complex queries. That's one trade-off in here. So it does lack the sophistication of relational databases. So if you want to do a group or sort or something like that, it becomes, you really don't want to use key-value databases to do that. So you'll notice that as I talk about these databases, I'm not only talking about the good features, but also some of the trade-offs that you have to use. The other issue with the key-value databases is as the volume of the data increases, the generation and maintenance of keys becomes more complex. Redis is a popular key-value database that you probably know. Memcached, there are more of these. Azure Table Storage is also a key-value database, and so on. So let's talk about document databases. Document-oriented databases, they store data in the form of documents, which encapsulate and encode the data. So you have standard formats for encoding like XML, JSON, BSON. BSON is actually the one for MongoDB. So each document, again, is accessed using the document ID plus the partition key. So you'll notice that the partition key is starting to become really important. And we'll talk about the partition key during our data modeling exercises. Document databases, most of them do offer some kind of a query language type, language to retrieve documents. You'll also notice that they are very flexible. The schema is very loose or flexible. So for instance, in the two documents that you see, the first one has employee ID with skills. The second one has employee ID without skills. And these two, they are somewhat similar, but also different schema, and they can be stored together. So that is the flexibility that they offered. One thing you have to keep in mind is that document databases, a fantastic thing they do is they not only can you access the documents using the document ID and partition key, but you can also run queries. So for instance, I can run a query on these two records that you're seeing on your screen, something like where location equal to Orlando. And then what it would do is it would go and look up the documents. When the documents are stored, each attribute, so for instance, employee ID, first name, skills, location, all of this are indexed. So it would see that when I run a query that says where city equal to Orlando, it will go and look for all the documents with the attribute city, and then it would go and compare the value for the documents that have city equal to Orlando and return them. So this would actually return all the documents that are associated with that value. But also there's a fantastic thing that you could do over here. So you can also run a query for these documents where you say that list all the documents where skills.skill name equal to C#. So in this case, because it has indexed the attributes, it will know that the first document has the skills field, and it has a field called skill name, and one of those has value C#. So it will return the first document. So that's a great thing about document databases, which you don't find that flexibility in a lot of relational databases. Like you cannot store, you'd have to store null fields to achieve these type of flexibility. So some examples of document-oriented databases are, RavenDB and MongoDB. Azure Cosmos DB has a SQL API that is also a document database. The next one I want to talk about is graph databases. And graph data, we talk about relational databases and NoSQL databases. So this leads us to believe that NoSQL databases are non-relational. Now, it is true that they're non-relational, but they're non-relational in the sense that you don't have a table-to-table relationship. But with graph databases, you can actually have relationship between two records without using tables. And this allows you to model a rich relationship between entities. So for instance, you can see that I'm in this example on the screen, I'm modeling all sorts of relationships between objects, and just by drawing a few lines and a few circles. Now, imagine having to create these type of relationships in a relational database. It would be a nightmare. The thing document databases do is they can achieve these type of super relationship by using vertices. Vertices are the circles or nodes, and edges. Edges are the arrows that you see on the screen. So vertices denote the discrete object, such as a person, place, event, and so on. And edges denote the relationship between vertices. So for instance, in this example, I have items like, X knows Y, Y is an employee of A, and so on. One thing to read up on is Dijkstra's algorithm, which is often a basis of a lot of graph databases. And Dijkstra's algorithm is basically used to conduct something called a breadth first search. And this allows you to find the shortest path between two nodes in a graph. And that's kind of the basis of all these graph databases, with the understanding that they all have evolved to have more complex algorithms since then. Again, if you have questions, drop them in the chat. Otherwise, I'll just assume I'm doing a great job and keep moving up. And the other type of NoSQL database is a column-oriented database. You may also, hear them referenced to as wide column database. And usually, these databases are they're basically optimized for queries of a large data set and stores column of data together. So, for instance, in this example, you see that the top tables show a simple example of how data is represented in relational database. In the bottom, you can see how the data is split up and stored by columns in column-oriented databases. So in column-oriented databases, you store all the values of a particular column together. So in a way, a column in a column-oriented database is the equivalent of a row in a relational database. So a relational database, a record is a row. In a column-oriented database, it's a column. And why is this important? When you store entire columns together, it makes it easy to retrieve these together. So this makes things like aggregation, sorting, and range operations really easy, because those values are kind of stored together on the same physical partition. So the other advantage is that, let's take an example like web views, right? So one of the biggest uses of column databases is for aggregating things like number of views on a product or something of that sort. So if the number of views is integer or long or whatever data type it is, since the data type is the same, the compression of the stored data is really easy. So you not only achieve efficiency in items like aggregation and sorting, but you also achieve efficiency in storage by compressing the data and uncompressing it real easy. Some examples of column databases are Cassandra and HBase. You probably heard of Cassandra. And finally, when I started giving talks on NoSQL databases, we did not have multi-model databases at all. But since then, the industry has evolved in the past few years, beginning with services like Cosmos DB and the other ones you see on the screen. In these, you support multiple models of databases. So the database, a multi-model database is a database system which is designed to support multiple data models. So in contrast, most database systems are organized around a single model, like a document-oriented database. But by comparison, multi-model databases are polyglot, which means you can create a instance to store document, you can create an instance to store graph, and you can create an instance to store key value. So the advantages of multi-model databases is that you have a single integrated backend, which means things like setup, maintenance, security, that is authentication, authorization, are all the same. So for instance, in Azure Cosmos DB, I can set up a document database, which is the SQL API. I can set up a table storage, that's the key value pair. I can set up a Cassandra, I can set up a graph instance. All of these by using a infrastructure as code like Bicep. I can run them with the Azure DevOps pipeline. I can deploy them on Azure under the same resource group. And I can assign the same type of maintenance scripts. And I can assign the same security. So I can use like Azure RBAC rules and assign, let's say, I have a RBAC group called data administrators. I can assign this group to all the 4 databases in a single operation. So that makes it extremely efficient and easy to set up and manage. While there are specialized multi-model databases like Cosmos DB, keep in mind that most databases like even SQL Server and Postgres and MySQL, Oracle, all the relational databases are also slowly starting to add JSON, XML, and other data types, and they are organically becoming multimodal. I always put this slide up because this is where I get a lot of my material from. So if you go to this website, db.io, you will find pretty much all the databases in existence. So it's like a database of databases. So definitely, if you have some time, feel free to review this website. Okay, so we talked about all these different types of databases. So what we're going to do for this section of the talk is kind of reduce our scope. Instead of talking all types of NoSQL database, we'll talk about the document-oriented NoSQL databases, and we'll talk about how to model data for these document-oriented databases. So one of the key features of these document-oriented databases is that the JSON documents, they lack adherence to a rigid schema. So one of the biggest thing about SQL is, you have a very rigid schema. So you have to adhere to that schema and you cannot violate it. But the document type databases are most flexible when it comes to that. So it's called, schemaless or schema-free data. So we'll definitely talk about why that is important. We'll talk about why database joins in relational databases are expensive and how to address that with denormalization. And then we'll talk about modeling relationships. So in SQL databases, you have one-to-one, one-to-many, many-to-many, and so on. So how do you model these relationships when you're storing those in document databases? So let's start with the schema-free data. So you'll hear this referred to in different terms. You'll see schema-free. You will see flexible schema. You'll also see loose schema. They all probably mean the same thing. It means the lack of strict adherence to a particular schema or to a rigid schema. The one thing about schema-free databases is the data is similar, but not the same. So let's take these two records. So the record on the left is kind of similar to the record on the right, except there's a little bit of embedding on the left for the contact details. And a NoSQL database or a document database would accept this fine. One thing I want to caution against is that you should, you should make use of the flexible schema feature of NoSQL databases. And I have worked with, hundreds of, not hundreds, but I worked with a bunch of developers who come from the SQL background who do not use the flexible schema feature. So, for instance, I've come across developers who would store these two documents in separate collections or separate containers, not in the same collection of containers. So you can absolutely store these in the same container because these probably belong to a user or user contact data type. But you should not store completely different, disparate data together. So you should not be storing a user record next to a device because those two are not the same. They're not similar. They're certainly not the same. So hopefully that's not too confusing. What I would say is data should be similar. It doesn't have to be the same, but it should not be completely disparate or completely out of the left field. So this kind of reflects the real life. So I work with in my past life, I worked with a lot of government clients. So for instance, the state of Florida and the state of Illinois may send drivers records, and these will have some common fields like driver's license number, but Florida might have something like whether this driver is allowed to operate in the Keys. And that's not going to be the case for someone in Illinois. You won't even have that field. But you have a few common fields like driver's license number, first name, last name. So those should be fine to store together. And that's exactly why you use document type databases. So the next thing I want to talk about is data normalization and why it's expensive. In relational databases, significant focus is placed around describing the entity and its relationship to other entities. After the relationships are finalized, items impacting performance, like indexes, are designed later. So when the schema is normalized, the data redundancy is reduced. This is great, by the way. Yeah, I don't want data redundancy, right? And the storage becomes more efficient. And finally, queries with joins bring the data back together. However, you speak to any DBA, and they'll tell you that joins are the biggest bottleneck. And if they're not designed properly, we can have a lot of issues. And the real life is you cannot always design them properly. You can never be 100% on that, right? And obviously, as we discussed earlier in this talk, this model does not scale horizontally. So the other thing with joins is there is no O of one complexity. So in a key value pair, you could retrieve something with the O of one lookup. So with joins, there is no O of one complexity because the process of joining the tables does not involve any kind of hash table type lookups. So that is completely out of picture. So the next thing is, okay, I cannot get O of one. Can I get O of one, O of n, where n is the number of records? But that's not possible either because you have joins. We have to use the O of n lookup for a filter like a where clause. So as a result, the best we can get on this is O of x log n, which means that x times log n, which means one of the fields, one of the tables has X records, and you can use that table as a basis, and then you use log of n lookup within the joins to achieve the data. So that kind of makes it more expensive. The other issue with a lot of normalization is that the design often doesn't account for null values, and the lack of incorrectly configured indexes in the database or null values in index fields depending on your database design, there could be null values in the index fields. Those can really impact your performance. So when you're doing a lot of joins, it hits the disk, and the disk I/O can significantly impact the join operations. So joins can increase random seeks, especially if you're jumping around reading parts of a large table. Since joins can be inefficient, particularly at scale, we will try a practice called denormalization. So denormalizing is where you, instead of storing it in tables, you take it and plump it into one document or a collection of documents. So this is the simplest form of denormalization. One-to-one is easy. You just figure out a record and you combine those two records, and that is a one-to-one denormalization. So I don't think we don't necessarily need to provide an example. This one is that you see on the screen is a one-to-many. So we have two different types of tables in here. The first one is a country table, and the second one is states or provinces of the country. So in this case, because we know that the country is the parent and the states are the child, we embed all the states within the parent country. So this is a one-to-many denormalization, and it's pretty straightforward. The difficult type of denormalization is the many-to-many. So this becomes really complex, and there are different ways to attack many-to-many records. Denormalization involving many-to-many records. Let's take an example of students have many-to-many relationship with courses. Like you have a university, and the students, one student can take many courses, and a course can have many students. So how do you, model this? So the first approach for this is called embedding. So in this method, we select one of the entities as parent and embed the other instance within the parent. So the many-to-many relationships means that some of the embedded instances will be repeated across different parent documents. So for instance, if I take a student and want to list the courses for that student, if that's the purpose of my query, then what I'll do is I'll create documents that have the student as parents and the courses that the student has taken as embedded as the child that is embedded within that parent. So in this case, you can see that this student has 3 courses embedded. And if you take the next student, let's say, John Doe could have the same 3 courses embedded. So there is redundancy, obviously, but this is kind of fine because the advantage of this approach is that a single document contains all the data associated with the parent, which makes the data retrieval a single operation. The disadvantage, obviously, is, like I said, that the embedded data can be repeated across different parent documents. So you want to make sure that the data that you're embedding is not data that is frequently updated. So for instance, if you take a student and courses, that student probably has that course for the entire semester. So it's not frequently updated. So during the semester, if I want to do lookups, it's okay for me to have this data embedded in there and for the data to be redundant across students because it's not going to change. So it's used in scenarios where it's fairly static, like looking up student information of courses or product listing info. So a lot of the product listing pages that you see on the internet are almost all of them are document databases with this type of embedding. Excuse me. The other approach to embedding is, this one is slightly tricky. So this is called referencing, and this is kind of similar to using many-to-many tables. So in this method, we select one of the entities as the parent and embed an array of references. So you have the parent, which is the student, and the child, which is the courses. But let's say the name of the course or some kind of property of the course constantly changes. Like let's say the course classroom timing or something of that sort. And I don't want to embed that full record in there. I simply embed a lookup value for that course within the parent record. And like I mentioned, this is another way to do it and use this approach when the data is frequently changing. So that kind of is a quick dive into data modeling for NoSQL databases. So let's talk about some questions you may have, like, should I switch from SQL to NoSQL? And then spoiler alert, yes, you should. And no, you should not just switch to NoSQL. You should use both SQL and NoSQL. You should always select the polyglot approach, use the best of both worlds. The second is, should I use database as a service for NoSQL data? And the answer is always yes. Never try to host your own distributed database system unless that's the primary objective of your business. So when selecting between SQL and NoSQL, here is a table that has some considerations. So you have to ask yourself questions like, does my, if I want to select a SQL versus NoSQL database, you have to ask yourself questions like, does my data fall anywhere on the outer ring of the 3V circle that we saw earlier? If it falls, if it is petabytes of data, if it's real-time data, if it's unstructured data, then you should be looking at a NoSQL database, not a relational tabular database. The second one is consistency. So am I okay with my database not being consistent? And that is a tough question. We all would like our database to be consistent, but in cases like social media likes, so what if my likes are not up to date and they update after a minute? Is that really the end of the world? Am I okay with trading that staleness for speed of response of the system? If I'm okay with that, I should be using a NoSQL database. The other question you should be asking, the SQL or NoSQL, is, do I want to host the database myself, or should I use a managed service? And finally, you should always design for polyglot persistence. So you should most likely be using both SQL and different families of NoSQL, like document and key value databases and so on. The other consideration is the total cost of ownership. NoSQL databases are, by their nature, intended for distributed hosting. Again, the question is, do you want to host it yourself in your data centers, or you want to farm it off to a provider like you have Azure, AWS, Google Cloud, or even if you take database providers like Mongo, they have Mongo Atlas. So you should most likely be looking at using those as opposed to trying to host a Mongo cluster in your own data center. Those should be extremely rare cases that lead you to create your own data center for hosting those. A good measure to look at is the total cost of ownership. So definitely look up, the different aspects of total cost of ownership, like paying rent for my building, paying for my own security versus, okay, I can, it's slightly more expensive in the cloud if you do just like spinning up a new database instance comparison. But I trade that off for not having to worry about physical security and so on, or compliance and all of that. Another thing to consider when picking NoSQL databases is consistency. So a lot of database systems make you pick. Okay, so I have a question. Curious where this TCO comes from. Many people I've talked about don't know the real TCO for traditional hosting. This is true. I think the best place to start is looking at capital expenditure versus operational expenditure, and this is a common term that I guess the bean counters in various companies look at as what is my capital, whether I have my own data center, that's considered as my capital expenditure versus if I have a cloud account that I can just swipe a credit card for. That's just operational expenditure. So a good example is, I have worked in situations where people have their own data center and they want to add a SQL database to an existing SQL server on a data center, and that's practically free. And then they come to the cloud, and to create the same one on the cloud, it costs them thousands of dollars. But then when you go back and look at the capital expenditure for creating an additional database, that included the room, the server, the heating, cooling, and so on, the physical security. So that capital expenditure really starts to add up, and it's probably 10x, 20x as compared to the thousands of dollars that they spend spinning up a new instance on Azure. So that is where I would say, if you compare those two, that's where the total cost of ownership comes from. And you're right that people don't think about it. It's like, when you have your own house and, you can paint the wall, but then, you had to kind of pay the closing costs on the house and so on. And so that makes it, you have to pay a lot of costs upfront versus when I rent an apartment, I cannot paint, I may not be able to make massive renovations, but then I can move on to a newer apartment if I want to. So that's kind of I guess that's the type of comparison I would make. Let's see, there's another question on here. TCO in the cloud is reduced by not having to buy servers upfront. Yep. And allows you to scale when you need to. You also don't have the cost of infrastructure personnel, correct? That have to set up and mount the hardware. Yeah, also keep in mind, you don't have heating, cooling costs, you don't have the costs for physical security and so on. So yeah, thanks, Steve. Thanks for chiming in.
I think something else that people forget, and since we're talking about databases, if you've ever tried to set up high availability for SQL Server, it's really hard. It is really, really hard. And if you do that, it's in Azure or AWS or any of the cloud providers, right? It's just, that's kind of done for you. And like what you don't want to do is set up high availability. It's really hard. And then because when you find out that you got it wrong is when you're down, right? And so if you set it up in a cloud provider, it's done for you. It's done by people that they've tested it. That's like all they do, right? And so you know that that's right. And I think that's one of the things, I mean, that kind of, it's a little bit away from kind of the dollars and cents conversation, but I think that's something else to think about, right? Is all these things like high availability and making sure that your backups work and stuff like that. It's easy to get that stuff wrong. And if you get it wrong, it's really disastrous. Right,
exactly. And thanks for that, David. I think the other thing I also look at is, is it crucial to your line of business? So for instance, like if I'm the Social Security Administration, I have a lot of data that I may not necessarily want to someone to have access to. So I prefer to store them on my own data centers because that's kind of, that data is my business. But, if I am, let's say, random company, let's say, I'm a company that, runs events, I am okay with that data being stored with, Azure or AWS because, I want to focus on running my business that conducts events, and I'm not really focusing on creating a data center and standing that up and putting guard in front of that because that's not crucial to my business. So that's how I look at it. There's another question. Relational database are table-based, NoSQL or more document, but I don't get why NoSQL databases can exist on multiple server nodes. Do you know what property of relational databases limits the? So the main answer is consistency is the ACID properties. I guess ACID is what I would say is your issue with relational databases and why they have to kind of be restricted to vertical scaling. Yeah, and Jim says if you don't test it, it's broken. So, I listened to this show called .NET Rocks, and one of the hosts, Richard Campbell, on there, he has a great saying, when you go into customer, ask them what is your restore strategy, not what is your backup strategy, because everyone has a backup strategy. Very few people have a restore strategy. So yes, definitely always test your backup, but then again, you want to make sure that you have a restore strategy, not just a backup strategy. Coming back to consistency, most systems make you pick between strong consistency, which is like the relational database type consistency, or eventual consistency, which means I have zero control, and at some point at infinity, if I have a constant stream of data coming in, my data is never going to be completely consistent. So, a lot of systems make you pick between this, but a lot of modern NoSQL databases, they offer a sliding scale. So for instance, Cosmos DB has something called a session consistency. So if I am, let's say I'm on UI and that UI connects to a social media system, and you're looking at, likes or comments or something like that, I can post to a comment, or I can like something, and I will be able to see that immediately within my session. So I know that my changes are getting reflected, but that does not mean it's visible to everyone else. So that is kind of session consistency. So you can see that your data changes are updated, but others, it might take a while for the data to sync up. So look for database systems that give you flexible levels of consistency. Latency is one thing you absolutely have to consider. How long do reads and writes take? Ideally, a modern NoSQL database system should give you latency of reads and writes in single millidigits, like less than 10 milliseconds, or it should be less than 50 milliseconds or something of that sort. Like you shouldn't be getting latency that's in 100 milliseconds or 500 or 1 second, because those are not acceptable in most modern scenarios, because you're trying to have fast responsive systems. Like e-commerce vendors, you have to have the whole page needs to load within 500 milliseconds. Guess what? If you don't do that, they just hit, customers just hit a tab and they go to your competitor's page because your page is slow. So they cannot afford that. So you have to have really low latency, ideally in the single or double digit milliseconds. And the other thing to look for is what percentile, not percentage, but percentile of the reads and writes fall within that latency. So those are the questions you should ask. The other thing you should ask is, let's say, I have a horizontal scaling when it creates new nodes, or I stand up a instance in a different region. How long does it take for these to become fully operational? And if the answer is more than X seconds, or in the case of a new region, if it's more than X minutes, then that's unacceptable. It should not take anything longer than a few seconds or minutes, depending on the scale of the new instances. Throughput is really something that you should look for when selecting a NoSQL database. And throughput is the amount of items passing through the system. So if you're reading and you're writing, the combination of that in and out is the throughput, because it's kind of the bandwidth. So it's the currency of modern NoSQL databases. And ideally, you should be able to provision a throughput, monitor whether it's working for you, and adjust it up or down. So the throughput is also important because NoSQL databases are often read heavy or write heavy. An example of a write heavy NoSQL database is a NoSQL database that collects data from a bunch of sensors that just come online and dump data into it. Example of a read-heavy NoSQL database is a one that has product listings stored in it. So all of this, they work on the basis of throughput. Availability. I don't know why I have an empty slide there, but we'll move on. Availability. Again, I often hear people proclaim that they have 99.59s of uptime. That's really hard because your system is only as available as the weakest component of the system. So you might have 99 percent uptime for your database, but if your load balancer is not that, then you cannot promise that. So again, be careful when you get numbers from database providers or even customers. So always verify those. We talked about partition key earlier. It is the single most important decision you will make in a NoSQL database. And the reason for this is most NoSQL databases, they look up the records with the O of 1 speed, like you want that speed, right? And the only way to do that is using either the document ID or the key value and the partition key, because then it directly goes to that partition and finds that key. If you don't provide that, then it does a scan of all the partitions, which you really want to avoid if possible. So geographical distribution as your system, if you have a nationwide or global system, geographical distribution becomes really important because let's say I have products and my system is based in the US and someone from Europe is accessing it, Australia. Your data can only travel as the max speed it can achieve is the speed of light, and we don't get anything close to that. So if you want to, the best way to achieve that is by putting the data source closest to the customer. So you may spin up an instance in Australia. That way they can access the data faster. So the question is, you should ask things like, if I provision an instance in Australia, how long does it take for that instance to become fully operational? If the answer is few minutes, then that's great. If the answer is a few hours or a few days, then probably not great. So again, the total cost of ownership, all of this comes into that, right? Like, how do you even start considering the total cost of ownership for a globally distributed system? This is why I tell people, like, don't try to host it yourself. Just use a provider. Also, you have another thing when distributing globally is you have to think about the read-write strategy. So if I have my instance in the US and Australia, what happens when the customer wants to write data to the database? Is the write going to come all the way to the US and then it sync across to Australia? Or is it going to write to the Australia instance and someone writes from the US, it writes to the US instance, and then it's eventually syncs? So that is whether you have a single primary database, a primary instance, or you have multi-primary instances. Okay, so that was kind of a whirlwind tour of NoSQL databases. And we discussed, what is NoSQL, what problems, some of the fundamentals. We talked about the different types. We talked about data modeling and some of the considerations for transitioning. And I want to remind you that, you should go polyglot and not just use SQL database or NoSQL database. Like, you should be ideally using SQL and multiple flavors of NoSQL. And you should probably always be using a database as a service as much as possible, unless that is your primary business, is that hosting data. So that is all I have.